Heavy metals. Heavy metals are generally defined as metals with relatively high densities, atomic weights, or atomic numbers. The criteria used, and whether metalloids are included. Example, a heavy metal may be defined on the basis of density, whereas in physics the distinguishing criterion might be atomic number, while a chemist would likely be more concerned with chemical behavior. More specific definitions have been published, but none of these have been widely accepted. The definitions surveyed in this article encompass up to 96 out of the 118 known chemical elements. Only mercury, lead and bismuth meet all of them. Despite this lack of agreement, the term is widely used in science. A density of more than 5 g/cm3 is sometimes quoted as a commonly used criterion and is used in the body of this article. The earliest known metals, common metals such as iron, copper, and tin, and precious metals such as silver, gold, and platinum are heavy metals. From 1809 onwards, light metals, such as magnesium, aluminium, and titanium, were discovered, as well as less well-known heavy metals including gallium, thallium, and hafnium. Some heavy metals are either essential nutrients, or relatively harmless, but can be toxic in larger amounts or certain forms. Other heavy metals, such as cadmium, mercury, and lead, are highly poisonous. Potential sources of heavy metal poisoning include mining, tailings, industrial wastes, agricultural runoff, occupational exposure, paints and treated timber. Physical and chemical characterizations of heavy metals need to be treated with caution, as the metals involved are not always consistently defined. As well as being relatively dense, heavy metals tend to be less reactive than lighter metals and have much less soluble sulfides and hydroxides. While it is relatively easy to distinguish a heavy metal such as tungsten from a lighter metal such as sodium, a few heavy metals, such as zinc, mercury, and lead, have some of the characteristics of lighter metals, and lighter metals such as beryllium, scandium, and titanium, have some of the characteristics of heavier metals. Heavy metals are relatively scarce in the Earth's crust but are present in many aspects of modern life. They are used in, for example, golf clubs, cars, antiseptics, self-cleaning ovens, plastics, solar panels, mobile phones, and particle accelerators. There is no widely agreed criterion-based definition of a heavy metal. Different meanings may be attached to the term, depending on the context. In metallurgy, for example, a heavy metal may be defined on the basis of density, whereas in physics the distinguishing criterion might be atomic number, and a chemist would likely be more concerned with chemical behavior. Density criteria range from above 3.5 g/cm3 to above 7 g/cm3. Atomic weight definitions can range from greater than sodium, greater than 40, or more than 200, i.e. from mercury onwards. Atomic numbers of heavy metals are generally given as greater than 20, sometimes this is capped at 92. Definitions based on atomic number have been criticized for including metals with low densities. For example, rubidium in group 1 of the periodic table has an atomic number of 37 but a density of only 1.532 g/cm3, which is below the threshold figure used by other authors. The same problem may occur with atomic weight-based definitions. The United States Pharmacopoeia includes a test for heavy metals that involves precipitating metallic impurities as their colored sulfides. In 1997, Stephen Hawkes, a chemistry professor writing in the context of 50 years' experience with the term, said it applied to metals with insoluble sulfides and hydroxides, whose salts produce colored solutions in water and whose complexes are usually colored. On the basis of the metals he had seen referred to as heavy metals, he suggested it would be useful to define them as all the metals in periodic table columns 3 to 16 that are in row 4 or greater, in other words, the transition metals and post-transition metals. The lanthanides satisfy Hawkes' three-part description. The status of the actinides is not completely settled. In biochemistry, heavy metals are sometimes defined on the basis of the Lewis acid behavior of their ions in aqueous solution as Class B and borderline metals. In this scheme, Class A metal ions prefer oxygen donors, Class B ions prefer nitrogen or sulfur donors, and borderline or ambivalent ions show either class A or B characteristics, depending on the circumstances. Class A metals, which tend to have low electronegativity and form bonds with large ionic character, are the alkali and alkaline earths, aluminium, the group 3 metals, and the lanthanides and actinides. Class B metals, which tend to have higher electronegativity and form bonds with considerable covalent character, are mainly the heavier transition and post-transition metals. Borderline metals largely comprise the lighter transition and post-transition metals. The distinction between the Class A metals and the other two categories is sharp. A frequently cited proposal to use these classification categories instead of the more evocative name heavy metal has not been widely adopted. A density of more than 5G/cm3 is sometimes mentioned as a common heavy metal defining factor and, in the absence of a unanimous definition, is used to populate this list and guide the remainder of the article. Metalloids meeting the applicable criteria, arsenic and antimony for example, are sometimes counted as heavy metals, particularly in environmental chemistry, as is the case here. Selenium is also included in the list. It falls marginally short of the density criterion and is less commonly recognized as a metalloid but has a waterborne chemistry similar in some respects to that of arsenic and antimony. Other metals sometimes classified or treated as heavy metals, such as beryllium, aluminium, calcium, and barium are here treated as light metals and, in general, are not further considered. The heaviness of naturally occurring metals such as gold, copper, and iron may have been noticed in prehistory and, in light of their malleability, led to the first attempts to craft metal ornaments, tools, and weapons. All metals discovered from then until 1809 had relatively high densities. Their heaviness was regarded as a singularly distinguishing criterion. From 1809 onwards, light metals such as sodium, potassium, and strontium were isolated. Their low densities challenged conventional wisdom and it was proposed to refer to them as metalloids. This suggestion was ignored. The new elements came to be recognized as metals, and the term metalloid was then used to refer to nonmetallic elements and, later, elements that were hard to describe as either metals or nonmetals. An early use of the term heavy metal dates from 1817, when the German chemist Leopold Gmelin divided the elements into nonmetals, light metals, and heavy metals. Light metals had densities of 0.865.0 G/cm3, heavy metals 5.30822.000. The term later became associated with elements of high atomic weight or high atomic number. It is sometimes used interchangeably with the term heavy element. For example, in discussing the history of nuclear chemistry, McGee notes that the actinides were once thought to represent a new heavy element transition group, whereas Seaborg and co-workers favored a heavy metal rare earth-like series. In astronomy, however, a heavy element is any element heavier than hydrogen and helium. In 2002, Scottish toxicologist John Duffus reviewed the definitions used over the previous 60 years and concluded they were so diverse as to effectively render the term meaningless. Along with this finding, the heavy metal status of some metals is occasionally challenged on the grounds that they are too light, or are involved in biological processes, or rarely constitute environmental hazards. Examples include scandium, vanadium to zinc, and rhodium, indium, and osmium. Despite its questionable meaning, the term heavy metal appears regularly in scientific literature. A 2010 study found that it had been increasingly used and seemed to have become part of the language of science. It is said to be an acceptable term, given its convenience and familiarity, as long as it is accompanied by a strict definition. The counterparts to the heavy metals, the light metals, are alluded to by the Minerals, Metals, and Materials Society as including aluminium, magnesium, beryllium, titanium, lithium, and other reactive metals. The named metals have densities of 0.534 to 4.54 G/cm3. Trace amounts of some heavy metals, mostly in period 4, are required for certain biological processes. These are iron and copper, cobalt, zinc, vanadium and manganese, chromium, nickel, arsenic and selenium. Periods 5 and 6 contain fewer essential heavy metals, consistent with the general pattern that heavier elements tend to be less abundant and that scarcer elements are less likely to be nutritionally essential. In period 5, molybdenum is required for the catalysis of redox reactions, cadmium is used by some marine diatoms for the same purpose, and tin may be required for growth in a few species. In period 6, tungsten is required by some archaea and bacteria for metabolic processes. A deficiency of any of these period 4-6 essential heavy metals may increase susceptibility to heavy metal poisoning. An average 70 kg human body is about 0.01% heavy metals, 2% light metals and nearly 98% non-metals. A few non-essential heavy metals have been observed to have biological effects. Gallium, germanium, indium, and most lanthanides can stimulate metabolism, and titanium promotes growth in plants. Heavy metals are often assumed to be highly toxic or damaging to the environment. Some are, while certain others are toxic only if taken in excess or encountered in certain forms. Chromium, arsenic, cadmium, mercury, and lead have the greatest potential to cause harm on account of their extensive use, the toxicity of some of their combined or elemental forms, and their widespread distribution in the environment. Hexavalent chromium, for example, is highly toxic as are mercury vapor and many mercury compounds. These 5 elements have a strong affinity for sulfur. In the human body they usually bind, via thiol groups, to enzymes responsible for controlling the speed of metabolic reactions. The resulting sulfur-metal bonds inhibit the proper functioning of the enzymes involved. Human health deteriorates, sometimes fatally. Chromium and arsenic are carcinogens, cadmium causes a degenerative bone disease, and mercury and lead damage the central nervous system. Lead is the most prevalent heavy metal contaminant. Levels in the aquatic environments of industrialized societies have been estimated to be 2 to 3 times those of pre-industrial levels. As a component of tetraethyl lead, 4Pb, it was used extensively in gasoline during the 1930s-1970s. Although the use of leaded gasoline was largely phased out in North America by 1996, soils next to roads built before this time retain high lead concentrations. Later research demonstrated a statistically significant correlation between the usage rate of leaded gasoline and violent crime in the United States, taking into account a 22-year time lag. The violent crime curve virtually tracked the lead exposure curve. Other heavy metals noted for their potentially hazardous nature, usually as toxic environmental pollutants, include manganese, cobalt and nickel, copper, zinc, selenium, and silver, tin, as organotin, antimony, and thallium. Heavy metals essential for life can be toxic if taken in excess. Some have notably toxic forms. Vanadium pentoxide is carcinogenic in animals and, when inhaled, causes DNA damage. The purple permanganate ion MnO4 is a liver and kidney poison. Ingesting more than 0.5 grams of iron can induce cardiac collapse. Such overdoses most commonly occur in children and may result in death within 24 hours. Nickel carbonyl 4, at 30 parts per million, can cause respiratory failure, brain damage, and death. Imbibing a gram or more of copper sulfate can be fatal. Survivors may be left with major organ damage. More than 5 milligrams of selenium is highly toxic. This is roughly 10 times the 0.45 milligram recommended maximum daily intake. Long-term poisoning can have paralytic effects. A few other non-essential heavy metals have one or more toxic forms. Kidney failure and fatalities have been recorded arising from the ingestion of germanium dietary supplements. Exposure to osmium tetroxide may cause permanent eye damage and can lead to respiratory failure and death. Indium salts are toxic if more than few milligrams are ingested and will affect the kidneys, liver, and heart. Cisplatin 2, which is an important drug used to kill cancer cells, is also a kidney and nerve poison. Bismuth compounds can cause liver damage if taken in excess. Insoluble uranium compounds, as well as the dangerous radiation they emit, can cause permanent kidney damage. Heavy metals can degrade air, water, and soil quality, and subsequently cause health issues in plants, animals, and people, when they become concentrated as a result of industrial activities. Common sources of heavy metals in this context include mining and industrial wastes, vehicle emissions, lead-acid batteries, fertilizers, paints, and treated timber, aging water supply infrastructure, and microplastics floating in the world's oceans. Recent examples of heavy metal contamination and health risks include the occurrence of Minamata disease in Japan, the Bento Rodrigues Dam disaster in Brazil, and high levels of lead in drinking water supplied to the residents of Flint, Michigan, in the northeast of the United States. Heavy metals up to the vicinity of iron are largely made via stellar nucleosynthesis. In this process, lighter elements from hydrogen to silicon undergo successive fusion reactions inside stars, releasing light and heat and forming heavier elements with higher atomic numbers. Heavier heavy metals are not usually formed this way since fusion reactions involving such nuclei would consume rather than release energy. Rather, they are largely synthesized by neutron capture, with the two main modes of this repetitive capture being the S process and the R process. In the S process, singular captures are separated by years or decades, allowing the less stable nuclei to beta decay, while in the R process, captures happen faster than nuclei can decay. Therefore, the S process takes a more or less clear path. For example, stable cadmium-110 nuclei are successively bombarded by free neutrons inside a star until they form cadmium-115 nuclei, which are unstable and decay to form indium-115. These nuclei capture neutrons and form indium-116, which is unstable, and decays to form tin-116, and so on. In contrast, there is no such path in the R process. The S process stops at bismuth due to the short half-lives of the next two elements, polonium and astatine, which decay to bismuth or lead. The R process is so fast it can skip this zone of instability and go on to create heavier elements such as thorium and uranium. Heavy metals condense in planets as a result of stellar evolution and destruction processes. Stars lose much of their mass when it is ejected late in their lifetimes, and sometimes thereafter as a result of a neutron-star merger, thereby increasing the abundance of elements heavier than helium in the interstellar medium. When gravitational attraction causes this matter to coalesce and collapse, new stars and planets are formed. The Earth's crust is made of approximately 5% of heavy metals by weight, with iron comprising 95% of this quantity. Light metals and nonmetals make up the other 95% of the crust. Despite their overall scarcity, heavy metals can become concentrated in economically extractable quantities as a result of mountain building, erosion, or other geological processes. Heavy metals are primarily found as lithophiles or chalcophiles. Lithophile heavy metals are mainly F-block elements and the more reactive of the D-block elements. They have a strong affinity for oxygen and mostly exist as relatively low-density silicate minerals. Chalcophile heavy metals are mainly the less reactive D-block elements, and period 4,6 P-block metals and metalloids. They are usually found in sulfide minerals. Being denser than the lithophiles, hence sinking lower into the crust at the time of its solidification, the chalcophiles tend to be less abundant than the lithophiles. On the other hand, gold is a siderophile, or iron-loving element. It does not readily form compounds with either oxygen or sulfur. At the time of the Earth's formation, and as the most noble of metals, gold sank into the core due to its tendency to form high-density metallic alloys. Consequently, it is a relatively rare metal. Some other noble heavy metals, molybdenum, rhenium, the platinum group metals, germanium, and tin, can be counted as siderophiles, but only in terms of their primary occurrence in the Earth, rather the crust. These metals otherwise occur in the crust, in small quantities, chiefly as chalcophiles. Concentrations of heavy metals below the crust are generally higher, with most being found in the largely iron silicon nickel core. Platinum, for example, comprises approximately 1 part per billion of the crust, whereas its concentration in the core is thought to be nearly 6,000 times higher. Recent speculation suggests that uranium in the core may generate a substantial amount of the heat that drives plate tectonics and sustains the Earth's magnetic field. The winning of heavy metals from their ores is a complex function of ore type, the chemical properties of the metals involved, and the economics of various extraction methods. Different countries and refineries may use different processes, including those that differ from the brief outlines listed here. Broadly speaking, and with some exceptions, lithophile heavy metals can be extracted from their ores by electrical or chemical treatments, while chalcophile heavy metals are obtained by roasting their sulfide ores to yield the corresponding oxides, and then heating these to obtain the raw metals. Radium occurs in quantities too small to be economically mined and is instead obtained from spent nuclear fuels. The chalcophile platinum group metals mainly occur in small quantities with other chalcophile ores. The ores involved need to be smelted, roasted, and then leached with sulfuric acid to produce a residue of PGM. This is chemically refined to obtain the individual metals in their pure forms. Compared to other metals, PGM are expensive due to their scarcity and high production costs. Gold, a siderophile, is most commonly recovered by dissolving the ores in which it is found in a cyanide solution. The gold forms a dicyanoorate, for example, 2O plus H2O plus 1/2 O2 plus KCN2K plus 2KOH. Zinc is added to the mix and, being more reactive than gold, displaces the gold, 2 plus ZnK2 plus 2O. The gold precipitates out of solution as a sludge, and is filtered off and melted. Some general physical and chemical properties of light and heavy metals are summarized in the table. The comparison should be treated with caution since the terms light metal and heavy metal are not always consistently defined. Also, the physical properties of hardness and tensile strength can vary widely depending on purity, grain size, and pre-treatment. These properties make it relatively easy to distinguish a light metal like sodium from a heavy metal like tungsten, but the differences become less clear at the boundaries. Light structural metals like beryllium, scandium, and titanium have some of the characteristics of heavy metals, such as higher melting points. Post-transition heavy metals like zinc, cadmium, and lead have some of the characteristics of light metals, such as being relatively soft, having lower melting points, and forming mainly colorless complexes. Heavy metals are present in nearly all aspects of modern life. Iron may be the most common as it accounts for 90% of all refined metals. Platinum may be the most ubiquitous given it is said to be found in, or used to produce, 20% of all consumer goods. Some common uses of heavy metals depend on the general characteristics of metals such as electrical conductivity and reflectivity, or the general characteristics of heavy metals such as density, strength, and durability. Other uses depend on the characteristics of the specific element, such as their biological role as nutrients or poisons or some other specific atomic properties. Examples of such atomic properties include partly filled d or f orbitals that enable the formation of colored compounds, the capacity of most heavy metal ions to exist in different oxidation states and therefore act as catalysts, poorly overlapping 3d or 4f orbitals that give rise to magnetic effects, and high atomic numbers and electron densities that underpin their nuclear science applications. Typical uses of heavy metals can be broadly grouped into the following 6 categories. Some uses of heavy metals, including in sport, mechanical engineering, military ordnance, and nuclear science, take advantage of their relatively high densities. In underwater diving, lead is used as a ballast. In handicap horse racing, each horse must carry a specified lead weight, based on factors including past performance, so as to equalize the chances of the various competitors. In golf, tungsten, brass, or copper inserts in fairway clubs and irons lower the center of gravity of the club, making it easier to get the ball into the air, and golf balls with tungsten cores are claimed to have better flight characteristics. In fly fishing, sinking fly lines have a PVC coating embedded with tungsten powder, so that they sink at the required rate. In track and field sport, steel balls used in the hammer throw and shot put events are filled with lead in order to attain the minimum weight required under international rules. Tungsten was used in hammer throw balls at least up to 1980. The minimum size of the ball was increased in 1981 to eliminate the need for what was, at that time, an expensive metal not generally available in all countries. Tungsten hammers were so dense that they penetrated too deeply into the turf. In mechanical engineering, heavy metals are used for ballast in boats, aeroplanes, and motor vehicles, or in balance weights on wheels and crankshafts, gyroscopes, and propellers, and centrifugal clutches, in situations requiring maximum weight in minimum space. A. M. Russell and K. L. Lee structure property relation seen non-ferrous metals. In military ordnance, tungsten or uranium is used in armor plating and armor-piercing projectiles, as well as in nuclear weapons to increase efficiency. In the 1970s, tantalum was found to be more effective than copper in shaped charge and explosively formed anti-armor weapons on account of its higher density, allowing greater force concentration, and better deformability. Less toxic heavy metals, such as copper, tin, tungsten, and bismuth, and probably manganese, have replaced lead and antimony in the green bullets used by some armies and in some recreational shooting munitions. Doubts have been raised about the safety of tungsten. Because denser materials absorb more radioactive emissions than lighter ones, heavy metals are useful for radiation shielding and to focus radiation beams in linear accelerators and radiotherapy applications. The strength or durability of heavy metals such as chromium, iron, nickel, copper, zinc, molybdenum, tin, tungsten, and lead, as well as their alloys, makes them useful for the manufacture of artifacts such as tools, machinery, appliances, utensils, pipes, railroad tracks, buildings and bridges, automobiles, locks, furniture, ships, planes, coinage and jewelry. They are also used as alloying additives for enhancing the properties of other metals. Of the 24 elements that have been used in the world's monetized coinage, only 2, carbon and aluminium, are not heavy metals. Gold, silver, and platinum are used in jewelry, as are nickel, copper, indium, and cobalt in colored gold. Low-cost jewelry and children's toys may be made, to a significant degree, of heavy metals such as chromium, nickel, cadmium, or lead. Copper, zinc, tin, and lead are mechanically weaker metals but have useful corrosion prevention properties. While each of them will react with air, the resulting patterns of either various copper salts, zinc carbonate, tin oxide, or a mixture of lead oxide, carbonate, and sulfate, confer valuable protective properties. Copper and lead are therefore used, for example, as roofing materials. Zinc acts as an anti-corrosion agent in galvanized steel, and tin serves a similar purpose on steel cans. The workability and corrosion resistance of iron and chromium are increased by adding gadolinium. The creep resistance of nickel is improved with the addition of thorium. Tellurium is added to copper and steel alloys to improve their machinability, and to lead to make it harder and more acid resistant. The biocidal effects of some heavy metals have been known since antiquity. Platinum, osmium, copper, ruthenium, and other heavy metals, including arsenic, are used in anti-cancer treatments, or have shown potential. Antimony, bismuth, gold, and iron are also important in medicine. Copper, zinc, silver, gold, or mercury are used in antiseptic formulations. Small amounts of some heavy metals are used to control algal growth in, for example, cooling towers. Depending on their intended use as fertilizers or biocides, agrochemicals may contain heavy metals such as chromium, cobalt, nickel, copper, zinc, arsenic, cadmium, mercury, or lead. Selected heavy metals are used as catalysts in fuel processing, synthetic rubber and fiber production, emission control devices, and in self-cleaning ovens. Oxide in the walls of such ovens helps oxidize carbon-based cooking residues. In soap chemistry, heavy metals form insoluble soaps that are used in lubricating greases, paint dryers, and fungicides. The colors of glass, ceramic glazes, paints, pigments, and plastics are commonly produced by the inclusion of heavy metals such as chromium, manganese, cobalt, copper, zinc, selenium, zirconium, molybdenum, silver, tin, praseodymium, neodymium, erbium, tungsten, iridium, gold, lead, or uranium. Tattoo inks may contain heavy metals, such as chromium, cobalt, nickel, and copper. The high reflectivity of some heavy metals is important in the construction of mirrors, including precision astronomical instruments. Headlight reflectors rely on the excellent reflectivity of a thin film of rhodium. Heavy metals or their compounds can be found in electronic components, electrodes, and wiring and solar panels, where they may be used as either conductors, semiconductors, or insulators. Molybdenum powder is used in circuit board inks. Ruthenium oxide-coated titanium anodes are used for the industrial production of chlorine. Home electrical systems, for the most part, are wired with copper wire for its good conducting properties. Silver and gold are used in electrical and electronic devices, particularly in contact switches, as a result of their high electrical conductivity and capacity to resist or minimize the formation of impurities on their surfaces. The semiconductors cadmium telluride and gallium arsenide are used to make solar panels. Hafnium oxide, an insulator, is used as a voltage controller in microchips. Tantalum oxide, another insulator, is used in capacitors in mobile phones. Heavy metals have been used in batteries for over 200 years, at least since Volta invented his copper and silver voltaic pile in 1800. Promethium, lanthanum, and mercury are further examples found in, respectively, atomic, nickel metal hydride, and button cell batteries. Magnets are made of heavy metals such as manganese, iron, cobalt, nickel, niobium, bismuth, praseodymium, neodymium, gadolinium, and dysprosium. Neodymium magnets are the strongest type of permanent magnet commercially available. They are key components of, for example, car door locks, starter motors, fuel pumps, and power windows. Heavy metals are used in lighting, lasers, and light-emitting diodes. Flat panel displays incorporate a thin film of electrically conducting indium tin oxide. Fluorescent lighting relies on mercury vapor for its operation. Ruby lasers generate deep red beams by exciting chromium atoms. The lanthanides are also extensively employed in lasers. Gallium, indium, and arsenic, and copper, iridium, and platinum are used in LEDs. Niche uses of heavy metals with high atomic numbers occur in diagnostic imaging, electron microscopy, and nuclear science. In diagnostic imaging, heavy metals such as cobalt or tungsten make up the anode materials found in X-ray tubes. In electron microscopy, heavy metals such as lead, gold, palladium, platinum, or uranium are used to make conductive coatings and to introduce electron density into biological specimens by staining, negative staining, or vacuum deposition. In nuclear science, nuclei of heavy metals such as chromium, iron, or zinc are sometimes fired at other heavy metal targets to produce superheavy elements. Heavy metals are also employed as spallation targets for the production of neutrons or radioisotopes such as astatine. Definition and usage. Toxicity and biological role. Formation. Uses.